Hello and welcome to another exciting session. This session will be great because we are going to talk about how an MCU communicates with the outside world. As usual, we approach a problem practically and in a simple way so that you can try it out whenever you like during the lecture. So without further ado, what is this lecture about? Well, this lecture is again about pointers. However, embedded systems allow us to have a slightly different point of view on those abstract variables, and hence it is easier to grasp what those variables are and how to use them. But enough said, let's dig in. What are we going to do in this session? First, we will have a look at Arduino and specifically at the commands digitalWrite and pinMode to set a practical example. We also discuss the requirements of those commands, that is, how much program memory they need and how costly they are in terms of clock cycles. We will continue by showing how the input and output ports work, or I/O in short. We are going to modify our example program and compare the requirements again. And we will introduce the AVR library, which allows developer to prevent introducing bugs and making the implementation more comfortable. We will end the session with a short recap and an outlook what will be next in the syllabus. Excited? Alright, let's get started. This is the Arduino chip, or more precisely, the ATmega328P, as it is written on its casing. It comes in various shapes, also called packaging. For instance, what you see here is the so-called DIP, or DIP, which stands for Dual Inline Packaging. It is easy to recognize due to the arrangement of pins in two lines left and right, like an insect with 28 legs. There are other forms of packaging depending on how much space is available. For instance, the Arduino Mini Pro is so small that the ATmega328P is directly soldered on the board, and it comes in a TQFP, which stands for Thin Quad Flat Package due to its squared shape. But no matter the packaging of your Arduino, the programming methods and its specifications remain the same. Let's have a look at the problem at hand that we are trying to solve, namely the blinking LED problem. It sounds very simple, and it is. But it also gives the opportunity to look at some of the fundamental optimization problems that we are going to discuss in this lecture. This image shows what pins have what meaning in the world of Arduino. For instance, if we access this pin 0 in the Arduino IDE, then we change the state of this particular hardware pin and decide if it supplies power or not. For most of those pins, we can determine the state and therefore drive sensors, make LEDs blink, communicate, or react to buttons. Most pins have multiple functions, which will be handled later in the course. No matter what Arduino you have, most have an LED on board, which is connected to one of the pins of the Arduino. If you have the Arduino Uno, you might have seen in the blink example that is soldered to digital pin 13, that is here. So that pin is connected to an LED, a resistor, and then goes into the ground. If you power on this pin 13, the LED will turn on. So how do we drive this particular pin from the software side? Here is the example sketch from the Arduino IDE. I just removed all the comments due to space constraints on the slides. There are two functions, setup and loop. In the setup function, the developer configures the pin as an output pin so that data can be written to it. In the loop function, which keeps repeatedly executing, the developer said that the pin should have power so that the LED is turned on, then wait for 1 second, turn it off, wait for 1 second again, and keep repeating this process. This example is straightforward, and if you have two LEDs that you would like to blink alternatively, it will be no problem. Just duplicate all the instructions for an arbitrary other pin pin number 12 for instance, and connect an LED to it. However, if something does not work, a common practice of debugging is to insert printfs to figure out what the values are. In Arduino, we do not have a keyboard nor a screen, so the serial interface will be an option. We configure the serial interface with a specific transfer speed. Here, 9600 symbols or bits can be transferred each second. When the LED is turned on, high should be displayed on the terminal, followed by the text low when the LED is turned off. Let's examine the requirements in terms of program memory and RAM. Remember, the program memory is very limited and amounts to 32 kilobyte, while the RAM is 2 kilobyte. The Blink program requires 924 bytes in total and uses 9 bytes for global variables. If 2 LEDs are made blinking, another 48 bytes of program memory is required. Interestingly is how the use of serial for debug purposes blows up the program by adding 1 kilobyte to the overall size. That is almost double of the program size for our intended purpose. Also, the question is, we do not use any global variables at all, so where are those 9 bytes coming from? Apart from those questions, let's have a look how many clock cycles are required to change the pin to be an output and how many does it take to change its state. As you can see, changing the pin to act as an output requires 42 cycles, while changing its state is 52 cycles. Coming to the debugging interface, a serial.begin, which sets up the speed and communication protocol, completes in 70 cycles, which is still okay. However, printing through the terminal seems to slow down our program significantly. The issue is that while the CPU is busy printing out the characters, it cannot do anything else. It sends a character, waits till it has been transmitted, and takes the next character. Therefore, the slower the transfer speed, the longer the CPU has to wait till it can move on to the next character in line to be transmitted. Have a look at the delay. A delay of 1000 waits for almost exactly 1 second, and around 16 million clock cycles passed within that second. We can say that the CPU is clocked at the frequency of 16 MHz, which is what is mentioned in the datasheet of Arduino Uno. So now we know how costly it is to use each of those instructions. Imagine that you have a lot of pins to drive and to set. The more you have to use, the slower will be your program. So the question is, can we do better? And the answer is yes, but we have to understand what happens inside our ATmega328P, or also called MCU, first. It turns out that we can do a lot better, but let's do one step at a time and address how pins are driven internally. Here's the picture again, showing how the LED is connected to the pin. But the question is, what happens on the other side of the pin? In this lesson, we have a look at how the pin can change its state so that it is able to turn on the LED. Here is a circuit diagram. Do not worry, it might look a bit complicated at first, but let's go through it step by step. There are 4 different regions. We have the data direction region in green, the write pin region in red, the read pin region in blue, and the sleep region in black. As the name suggests, every region has its dedicated purpose. There is also another region, PUD, which we will skip for the time being. It is basically a functionality to activate a pull-up for this pin, which is used by some of the communication protocols. We are going to discuss those later in the course. Let us concentrate on the data direction region first. Here, the data direction is a bit magnified. It consists of a flip-flop, which holds the state of the data direction. You might have already guessed it. This flip-flop determines if the pin is an output or only an input pin. Hence, if you write pinMode in your code, you access this particular flip-flop of a pin. What does this flip-flop do? Well, it drives this buffer over here. This buffer acts like a switch. Hence, if the data direction flip-flop stores a 0, then this switch is open and the pin cannot be written. I mean, it can be written and the flip-flop in the write pin section will change its state. However, the output of this flip-flop is disconnected from the pin only if the data direction flip-flop is set to 1 and this switch is closed. The buffer connects the pin to the write pin section. So as a summary, the pinMode controls the green data direction section of the pin, while the digitalWrite controls the write pin section in red. What about the lower part? Here we have the read pin section in blue and the sleep section in black. First, let's talk about the read pin section. When we follow the blue wire from the pin, it passes through the sleep section and faces the synchronizer. Synchronizers are interesting hardware components which allow signals to cross into the clock domain of our MCU. If we want to read if the pin is high or low, this signal might change at any point in time. These flip-flops in the synchronizer synchronize the signal change with the clock of the MCU to avoid stability issues. After passing the synchronizer, the signal is facing another buffer right here. This buffer acts as a control to access the data bus, the big fat line on the right. Only if the instruction digital read is encountered in the program, the value should be read. That leaves us with the last section, the sleep section. What are those triangles here? This is actually a switch, which means if the sleep signal is high, the blue wire is severed and the synchronizer is separate from the pin. Instead, this transistor here becomes active and actively pulls down this wire to the ground. Hence, it becomes a 0, no matter if the pin is driven by a sensor, for instance, or not. That means that if sleep is active and digital read is encountered, always a 0 is read. What we also see is that a pin can always be read, but not always be written. Only if the data direction is set properly, the pin can be written too. That means even if the pin is configured as an output, you can still read from the pin. Try it out. That circuit diagram gives us a short overview, and it is already quite complicated. Every pin has its very own data direction, write pin, read pin, and sleep section. So, if there are 8 pins, those 8 pins have 8 data direction, 8 write pin, 8 read pin, and 8 sleep sections in total. All 8 pins are summarized and create a so-called port. An MCU might have several ports to control many pins. The flip-flops controlling the data direction are named DDR for Data Direction Register. The lowercase x, like here, or in this line, indicates the port number, since we can have many ports. The group of the flip-flops that handle the read pin sections are called PIN or pin, and the register that is responsible for writing data to the port's pins is referred to as port. In the next session, I will show you how you actually access those registers DDR, pin, and port that we had earlier. I mean, the purpose is to use them for your projects, so there should be a way to interface those registers with your software, right? In this session, I will explain how a developer gains access to the pins and can read or write data from or to them. Let's have a look at port B, whose pins are marked in this example. Consulting the datasheet of the ATmega328P, it shows the registers and their names. I'm attaching the datasheet to the resource folder of this lecture for your convenience. So for our port B, we have a register called port B, which is read and writable with a default value of 0 for each of the pins. This default value is the value that the register has after a reset or power up. That means a 0 is written to the port in case the data direction register allows us. Let's have a look. Here is the DDR. Each bit is also read and writable and its default value is 0. That means that all pins are configured to be inputs only, and writing values to port B will not show any effect. The datasheet also mentions our pin B, which stores the values if we would like to read incoming data from this pin. The question is now, how do we write anything to, for instance, the registers DDRB or port B? To answer this question, we have to understand memory space. For the ATmega328P, the entire memory is accessible. As you can see, the CPU inside the ATmega328P has 32 registers starting from address 0 to address 1F in hexadecimal format, which is 31 in decimal, hence 32 addresses for 32 registers. There are also 64 I/O registers followed by 160 extended I/O registers before the RAM starts. Having worked with PCs, a developer usually assumes that the RAM is organized from address 0 to the maximum address. However, in embedded systems, addresses might not point to RAM only. For instance, in this example, accessing address 1 or 0001 in hexadecimal format does not refer to the SRAM, but to the second register in the CPU. Why did the hardware engineers do that and make it so complicated? Well, it becomes very useful if you want to access pins in ports, for example. The entire memory space is continuous, and the same methods can be used to access ports, memory in SRAMs or registers. So it becomes quite easy to develop programs. Let's have a look at our port B example and back to the reference manual. Here, let's say we would like to access DDRB first. Since we know that the memory is continuous, this particular register must have an address, right? It turns out it has, and it's mentioned here in the brackets. It is 24 in hexadecimal format. So accessing address 24 will not read or write to the SRAM, but to this particular register. Cool, isn't it? So let's see how we can do that in our C programming. We would like to turn on the LED that is connected to pin PB5. So it belongs to port B and there to the 5th pin. Please note that the count starts from 0, so it is the 6th pin actually. A peek into the reference manual reveals the address that we need to access the required registers. That is DDRB to configure the pin to be an output pin and port B to write to it. So let's do it. We define two variables here. Those variables are pointers since they contain addresses, hence the star in front of the variable name right here. Since the DDRB is accessible at address 24 and port B at address 25, we directly set those addresses here. We would like to configure the data direction first. Hence we take our variable ddrb, dereference it, so that whatever we write to it does not go to the variable which resides in SRAM, but to the actual register that it points to. Or, in other words, write to the memory location that is accessible through address 024. Since we want to have the 6th port of the data register configured to be an output port, we just count through the bits and set the desired bit to 1. Remember, the counting starts from 0, so bit number 5 needs to be set. You might ask what the pipe in front of the equal sign means. That is an OR operation. So we read the values of ddrb and bitwise OR them with 0010, 0000. Remember, one pipe means bitwise OR, same as the ampersand sign, which is a bitwise AND. So we leave the other values of ddrb untouched. You might ask, why do we do that and do not set the entire port to be an output? Well, in larger projects, the other pins might be connected to other peripherals such as communication devices and sensors, which are developed by someone else in your team. Fiddling with pins that are not used by yourself is generally a bad idea, since you mess probably up the communications for someone else. On the other hand, you would not like that someone uses your pins either, so as a generic rule of thumbs, do not touch what does not belong to you. Moving on, once the pin is configured to be an output, let's turn it on. Similar to the line above, we take the values of port B, OR them with a bit mask that powers on our pin. Let's try it out. Fire up your Arduino IDE, copy this code, and be hopefully amazed. You know what? Let's rewrite our blinking LED program. This is the VirtualBox environment in which I demonstrate the programming session. It is a normal Ubuntu with long-term support, and I already installed everything that you require for this course. For instructions how to download this environment, please refer to the resources folder attached to the session. The advantage is that you do not have to download nor install any software such as the cross-compiler for Arduino, but can just dig in. In the session, I'm going to use the Blink example to demonstrate how to move away from the Arduino library. First, open the example. You find it under File, Examples, Basics, and Blink. I already opened here, I just removed the comments due to space constraints. We have two functions here, the setup function and the loop function. The setup function is executed once at the beginning, and in this we set the LED built-in pin to be an output. In the loop function, repeatedly, we turn on the LED, we wait for 1 second, we turn off the LED, and we wait again for 1 second. To move away from the Arduino library, we need access to two registers, namely ddrb to configure the pin to be an output, and port B to turn the pin on and off. As discussed in class, port B is accessible through address 25 in hexadecimal, and ddrb is accessible through address 24. So we need to have two variables with these addresses inside. So let's implement this. So first, I have an unsigned char to port B, which is an address, and I set this to 25 in hexadecimal format. I also have to configure the data direction. Therefore, I need access to ddrb, which is available under the address 24. So I do the same as in line 1 now. Unsigned char. Let's call the pointer ddrb and set it to 24. To modify the values that are stored in ddrb, I have to dereference ddrb and set the desired pin to 1, which I do here. So I OR it as discussed in class with itself and set the 5th pin to 1. 20 in hexadecimal format is equivalent to the following binary presentation. 0, 0, 1, 0, that is the 2, and I make a space here for having a better overview. 0, 0, 0, 0. This is the 0th pin, 1st, 2nd, 3rd, 4th, 5th. This line has the same functionality as this line now, so we can remove it. Going to the digital write here, which we have to rewrite. So I have the port B, which I dereference again, and set the desired pin to 1. So I OR it with itself and set the 5th pin to 1. Now this line has the same effect as this line, hence I can remove it. Now I have to turn off the pin. That means I have to access again the values at address 25, but this time I have to reset the pin. That means I have to end it with the inverted value of 20 in hexadecimal format. Let's remove it, compile and upload it. As you can see, we need now 640 bytes instead of 940 plus. Let's upload our program and see if it works. And does it work? If it doesn't work, please check if you made any mistake in these lines. So what are we doing in this loop function? First, we power on the pin so that the LED is turned on. Then we wait, after which we turn off the pin and we wait again for a second. As you can see, every second the state of the pin toggles. So instead, we can toggle the pin and wait for a second. But for that, we require a bitwise toggle operator instead of the bitwise OR and AND in our current implementation. Fortunately, there is one. It is the exclusive OR or XOR operator. Here is the truth table for XOR. As you can see, XOR returns 0 if either both A and B are 0 or A and B are set to 1. That means if they are different, then the XOR results in 1. So what can we use that for? There are two options in our implementation. Either the pin 5 is powered or it isn't. We need to XOR the current value of port B with a constant that has the bit set at the 5th position. Hence, if PB5 is 0 and we XOR PB5 with that 1, we get 1, turning on PB5. Or if the pin is turned on and hence PB5 is 1, we XOR that with 1 again and the 1 in the constant and we obtain 0. In the end, that toggles the pin. Let's head over to our program and add this optimization. Now we have to re-implement the body of this loop function. Instead of turning on the LED and turning it off, we just toggle it by replacing this OR operator by an XOR and removing these lines. Currently, the program needs 640 bytes. Let's compile and upload it, and let's see what the size is now. As you can see, it is only 602 bytes, so we save again another 40 with the same functionality. So why do we go through such an exercise? Well, let's see how our changes and removal of digitalWrite and pinMode affected the requirements of our program. As you can see, the requirements are reduced by approximately 30%, which is significant for such a small program. Even if you want to make more LEDs blink, we just have to change the bit mask, as we will see in the exercises. There won't be any increase of resources. What about the number of clock cycles? Is our program faster now? Yes, and that too by a magnitude. Instead of spending 52 cycles to write to a pin, we need only 2 cycles, namely 1 cycle for reading the port and 1 for performing the XOR and writing back the new value. It can be even shortened to one cycle only if we do not care about the other pins and just write the new value to it without reading port B. Even changing the data direction comes down from 42 cycles to only 3. Another advantage is that we can use different operators to achieve our desired goal. While digitalWrite allows to set or reset a pin only, we can read, perform an operation such as XOR, OR, and more, and write back the new value in a single line of code. What if we want to write to 2 pins of the same port? In Arduino, we need 2 digitalWrites. Here, we need only one port B assignment. So, why does pinMode and digitalWrite need so much computational resources? Well, Arduino does a lot of checking when you use, for instance, digitalWrite, such as, is this pin really an output pin, etc. These checks need time and program space. That might be a good idea for beginners, but we are experts now, and we know what happens inside the MCU, right? So we can save the resources and do it ourselves. Great. So we sped up our program, which might not be visible to us at the moment, since we cannot distinguish if a command executes in 10 microseconds or only 1. However, you might have a big project which runs on a limited power resource such as a battery. Every saving adds up and allows us to sleep longer, saving even more battery life. More about it later in the course. For now, is there a more comfortable way to write our programs? And do we have to remember all those addresses? Obviously not. But let's talk about that in the next session. And do not forget to complete the exercises to get used to the programming. Let's have a look how we can make our programming more comfortable without remembering all those addresses and checking them in the reference manual. Fortunately, the AVR library is available for our ATmega328P. It already predefines most, if not all, addresses for the registers available in our MCU. For instance, instead of declaring DDRB as a pointer and setting it to 24, the developer can just use DDRB in capital. Easy, isn't it? So the entire program from earlier becomes like this. But is that all? Obviously not. Another pain is the counting of bits and setting the right bit in the registers. Often, bugs are introduced because either the data direction register is misconfigured or the wrong pin is powered. To prevent this, the AVR library gives us a macro _BV, which does the bit shifting for us. Keep in mind that a macro is a preprocessor definition, so it does not add any computational overhead. Let's combine these comfortable functionalities and let's see what can we do with them. Here are some examples. So for instance, in line 1, without counting if the right bit is set, the developer used the BV macro to set the 5th bit in DDRB, which is also connected to the onboard LED. Or in line 2, the 5th bit of port B is XORed with itself. That statement is the same as using 1 and shifting it by PB5 positions. Cool, isn't it? No more counting. I can also set 2 bits in the DDRB without any computational overhead. First, the preprocessor takes care of the BV macro and the compiler recognizes those constants and ORs them for us during compilation, so that the MCU does not have to do it every time. Line 8 shows an example how a bit can be cleared. So let's say the 6th bit of port B should become an input pin only. Hence, the 6th bit of DDRB needs to be cleared without touching any other pin. So here, the preprocessor shifts a 1 for DDB 6 positions and then inverts the entire 8 bits. If the result is bitwise ANDed with the values of DDRB, Wherever the bit mask at that position is 1, the DDR-B bit remains the same. If the bit mask has a 0, the bit of DDR-B is cleared. Line 13 shows how a single bit can be read from a port. We read all values from the entire port at once and perform a bitwise AND with the pin that we need. That might be one bit, multiple bits in various positions, or the entire port. In the latter case, obviously no ANDing is required. Before we dive in and change our program, we have to lose a few words about a function call that we neglected till now, the delay function. It is an Arduino function and quite costly in terms of program memory space and hardware resources. Having a look at the source code, the path is given in a footnote. You can see that it consists of a while loop. Each iteration of the while loop takes 1 millisecond. The question is now, how is this 1 millisecond measured? The only source that has a notion of time is the clock frequency. The while loop uses built-in hardware timers to measure this 1 millisecond. A hardware timer is basically a counter incrementing its counter value at fixed time intervals. More about that later in the course. For now, it is sufficient to know that we have 3 counters in total and delay occupies one of them. In addition, while the timer value is read, the interrupts are disabled. In contrast, is the _delay_ms function that is supplied by the AVR library. It consists only of a loop with a fixed number of instructions. Here is the trick. Since the number of instructions in a loop and loop overhead are known, so are the number of required clock cycles. At the frequency of 16 MHz, the ATmega experiences 16 million clock cycles every second. So the question is now, how many iterations does a loop have to execute to get the desired waiting time? A big advantage over the delay loop in the Arduino library, it is timer independent. So we can still use that timer to do other stuff. Plus, interrupts are executed as usual. More about the beauty of interrupts later in the course. As we will see in a minute or so, replacing the delay by _delay_ms saves us another 200 bytes of code, which is quite substantial considering that delays are often used in embedded systems. Let's make good use of the new comfortable functionality. Head over to our blinking LED example and let's implement them. This is the last practical session for this chapter before I hand you over to the exercises. Now we would like to use the AVR library for our blinking example. The AVR library already defines macros for the pointer to DDR-B and the pointer to port B. Therefore, we don't have to remember these addresses any longer, and we can remove these lines. The macro for dereferencing DDR-B is DDR-B in capital. Same as well for port B. It is port B in capital letters. In addition, I'm setting the 5th bit of DDR-B here to configure this pin to be an output pin. However, I don't want to count any longer, and therefore I use this _BV macro. And it's the 5th pin of DDR-B. Same as valid for port B. However, this time it's the 5th pin of port B. Therefore, it's _BV port B5. In addition, we have to replace the delay function, which comes from the Arduino library. The equivalent function call in the AVR library is _delay ms. Before compilation, let's have a look at the program space requirements that this program currently needs. It requires 602 bytes of program memory. Let's compile it. As you can see, now it needs only 474 bytes, a significant reduction once again. Let's upload this program and let's see if it still works. Currently, we do not use any functionality of the Arduino library anymore. We removed delay, digitalWrite and pinMode and optimized our program. So the question is, why do we still need the Arduino IDE? At the moment we need it because it allows us to compile our code comfortably. However, from the next chapter onwards, we won't require the IDE any longer. But do not uninstall it just now. We still need the compiler that comes with it. So what have we learned in this session? We had a look at the internals of the ATmega328P and saw how the pins actually work. We learned how we can access registers using addresses and pointers, and also learned that the memory of many embedded systems is continuous, including the SRAM and the I/O controlling registers. We also introduced some of the more comfortable functionalities the AVR library has to offer. So what is next? In the next chapter, we will handle the topic how to write programs without the use of the Arduino IDE. We have to talk about makefiles so that we do not have to remember all the parameters to compile our programs for Arduino and to speed up the compilation process. So stay tuned, it will be very exciting. Before closing the chapter, on a personal note, I would like to hear from you how you liked this course so far. I'm trying to keep the course entertaining and practical, but maybe you found room for improvement. I would be happy to hear from you, and even happier if you could let others know what you think about this course. And with that, see you in a bit, and thanks for watching.